We have derived the expression where concentration of H plus at the interface is H plus in the bulk minus 1 minus gamma I delta over F times D H plus, right? You guys correct me if I'm missing something, and metal lines at the interface is metal lines in the bulk minus gamma I delta MF DM plus, right? Basically what it really means, there will be some gradient of the concentrations for H plus at the interface versus the bulk, and same for the metal ions, right? Okay. And we said that because this is going to be much lower than this, that means that the pH at the interface will be much higher than the pH in the bulk, right? And then we said if we are looking at the Fourier diagram for typical metal, whether it's a cobalt, iron, or nickel, it's going to look something like this, where this is the nickel, this is for example nickel 2 plus, and then this is nickel, but then here's the nickel hydroxide, nickel higher oxidation states, etc. And that's the problem, because if we think we are applying potential and we are sitting here depositing nickel at the interface, we might be actually also getting some nickel hydroxide precipitating. And because of that precipitation process, we said that usually our thin films of these metals are not so pure. Now, we give you an idea when we talk about solubility, what kind of numbers we are talking about when it comes to these metals, so you understand where the problem is. So, if this is the metal, and this is the Kp value, which is the product of solubility, and you know that Kp is equal to metal concentration times the OH minus concentration power m for any of these hydroxides, which are all 2 valent. And so for basically metal hydroxide, I'm just going to give you an idea so you understand. If this is a cobalt hydroxide, the Kp is of order of 2.5 times 10 to the minus 16, right? Then iron 2 hydroxide, Kp is of order of 7.9 times 10 to the minus 15, right? Then for nickel hydroxide, it is 2.8 times 10 to the minus 60. So you can see roughly they are about the same order of magnitude. Let's say iron hydroxide a little bit higher number than these two, but overall we are talking about the solubility of this hydroxide that is relatively the same, right? Now, let me give you a catch here. If you look at the iron 3 hydroxide, so this is iron 3, this is 3 here, right? The product of solubility is 6.3 times 10 to the minus 38. 38, minus 38. You can see that it is about 20 orders of magnitude, more than 20 orders of magnitude, smaller than any of these hydroxides, any. Iron 3 hydroxide. Now, I sent you some material, and we discussed yesterday this homework problem where you plot product of metal times the OH minus concentration at the interface. As a function of some of this, you're going to come up with some interesting things. But in reality, if you look this is 10 to the minus 16, for example, right? So that means that, for example, if I have cobalt, let's say 0.1 molar, that is 10 to the minus, let's say 15. Square root of 10 to the minus 15 is the order of 10 to the minus roughly 7. So that means that cobalt hydroxide, roughly, according to Pobre diagram saying for iron hydroxide and nickel hydroxide, will not show up unless you exceed pH around 7. And let's say you have some significant depletion. Let's say you're doing the position at pH 2, right? Because this is pH scale. That means you really have to deplete from 10 to the minus 2 molar, which is in the bulk in terms of H plus, to get to 10 to the minus 2. You have to deplete for 5 orders of magnitude to move effectively from this place to the place where you're going to have an issue with hydroxide precipitation when it comes to these 2 divalent hydroxides, right? It is possible, and especially it is possible if you do the position with pH 3, 4, and maybe 5 already, you're pushing the limit. But in general, what we really do to avoid the problem with this is that we like to stick around below 4, right? We like to be with pH below 4 when we do electrodeposition of these types of alloys with cobalt, nickel, and iron magnetic films and so on. And we don't like to go and push the limit close to the fact that we are exhausting all the H plus at the interface. But, you know, we try to design the process where the hydrogen evolution reaction is not so abundant, meaning that basically we will hardly get here. You could, but it's typically process itself. You have to really abuse it to get an issue with this precipitation here. Okay? Well, why I mentioned iron 3? Well, most of the alloys we talk about, which are today commercially, is nickel, iron, where the iron is 0.2, this is 0.8. It's famous permalloy. Then you have nickel 0.45, iron 0.55. Then you have cobalt, nickel, iron in different values, you know. They have a cobalt, iron. But the commonality among these magnetic alloys that we're in use today for different applications, magnetic recording, flux guides, whatnot, you know, MEMS, is that you have iron in there, which means the source of iron in the solution is iron 2 plus iron. Okay? All right. Now, what you don't know, and I'm going to tell you, is that if you have a solution exposed to the air, this solution is in equilibrium with the pressure, which is typically 1 atmosphere, and that means there will be some equilibrium solubility of the gas above the solution inside of the solution. For example, when we talk about oxygen, which is the case we want to discuss here, oxygen concentration at 1 atmosphere in solution that is open to the air is about, I think, 4 times 10 to the minus 4 molar. Something of that order, 10 to the minus 4. So it's real. Oxygen is dissolved in your solution no matter what you want to do. Now, if you want to get rid of it, it's not so easy. You can do chemical way, putting some oxygen scavengers, which are the typically substances that convert, that are oxidized by oxygen and so on. But if you simply have a solution, whatever you do in a solution to remove oxygen, if you don't do anything here, there will be more oxygen coming from the air, right? So then you can do nitrogen trapping, which means you fill this with nitrogen, and so then there's no oxygen above the solution, and that helps a little bit, right? But there are more problems. So the first problem is obviously oxygen in the solution plus iron 2 plus gives you iron 3 plus water here plus or actually let's say we are at low pH, so it's actually H plus, right? So H plus whatever. You get H3 and then you get H2O, and because we have H2 here 2, then 2, and there will be 4 H plus. Okay, so what really happens is that this oxygen oxidizes iron 2 to iron 3. At the same time, it gets reduced to OH plus OH minus, something like that, right? Let me see if I'm doing this right. So then 2OH minus. Am I right? Yes. Yeah. 4, 6, that's 6 here, right? Okay. Did I do this right? All right, something like that, right? So what is the really important thing is that oxygen dissolved in the solution oxidizes iron 2 plus to iron 3 plus. That's the process that happens no matter what you do, unless you put some nitrogen trapping and deaeration, etc., etc., etc. That's one problem. So let's say you solve this by putting nitrogen trapping here, right? You have another problem. In your electrochemical cell, let's say you do the position here, this is cathode, and this is a negative potential, but then this is an anode. Among other things that happens, here you will be having iron 2 deposition, but the problem here is that you're going to have iron 2 plus going to iron 3 plus electron. So actually on your anode you're going to be oxidizing some iron 2 plus. Now you can solve this problem by putting some kind of a membrane here that only lets some specific ions and then no iron passes through, etc. What I'm trying to tell you is that if you try to address this problem, it actually becomes quite complicated and expensive. It's not that you cannot address the problem of iron 2 conversion to iron 3, but it's not that easy, and I cannot tell you how this is done because I have trade secrets which I cannot discuss, but obviously it can be done, it requires more attention to the chemistry of the solution. It requires more attention to the fact that what you do is allowed. For example, what you can do to convert iron 3 to iron 2 is basically just submerge from time to time piece of cobalt, for example, and cobalt will react with iron 3 plus, and cobalt will go to cobalt 2 plus, and iron 3 will go to iron 2. The only thing is that what you're going to get is some dissolution of cobalt in your bath, and whether you have to have cobalt or not, and so on. So I'm just giving you an idea. There's a way to handle this problem, but it's actually getting complicated. All right. But the main thing is, in normal case, you're dealing with this, which is 10 to the minus 38 product of solubility. Now, that's extremely, extremely small product of solubility. Although this is 3, if you say, let's say iron is 3 plus is equal to 10 to the minus 6 molar concentration. That means that what is left is 10 to the minus 32. If I take the third root of 32, which is basically, or order of 10 to the minus 11, is the concentration of OH that is allowed. What I'm trying to tell you, POH 11 means that pH is 3. So if the pH is 3 and it goes a little bit off 3, you're going to start precipitating iron 3 hydroxide. And you only have 10 to the minus 6 molar concentration, which is really, really small. If you have, let's say, 10 to the minus 5, that's going to be 10 to the minus 33, third root, it's 11. So what I'm getting is that because this is so small, you're super sensitive to a very small concentrations of iron 3 plus in your solution, because it will cause precipitation, not only in the bulk, which is the end scenario, but because what we just discussed, that this and this is different than the bulk, your precipitation of iron 3 hydroxide will be affecting your process before you even see anything wrong with the solution. And when you see something is wrong, that means the solution looks like a crap. You can see visually rust type of the color. That's end of the process. Now, that means that before you even see visually something is wrong with your solution, your process could be way off and you could be dumping a lot of oxide in any of these alloys and so on. And they might not have exactly property that you want to have. Now, in industry, or when you do research, what you should understand is that ideality is rarely achieved. And so, most of the time, if these alloys here have oxygen percentage maybe 1 to 2, it's tolerable because the magnetic properties will not be significantly affected. But if this goes to 5 to 7%, suddenly everything changes. Now, from this being okay to this is a very small degree of freedom that you have in your process. This means that you're not going to have any device working. This means you're going to have probably 100% devices working. And this is why we're talking about this in more detail, so you understand. Now, let me reverse the story, just tell you a little bit something else. For example, what David is doing for his PhD is he's trying synthesis of these magnetic alloys, and he's trying to keep them magnetically good, but he's also trying to put some controllable amount of oxide phase in order to keep resistivity high, because these magnetic alloys require high resistivity, high moment, and so on. Right? So it's not always that you want to minimize this. Sometimes you want to have a little bit of oxygen because the scattering phase for electrons and maybe resistivity goes up. But there's a lot of things that by knowing this process you can design. And I'll give you a lecture next time just to show you how we can play the game with this thing and actually get some kind of phenomenal sensors, which is not a part of the material for this class, but I just want to give you an illustration. But let's say for the further discussion, we want to figure out how we can actually design the process for the known amount of iron 3 in the solution that will actually be tolerable, and what are the boundaries and how we can calculate these boundaries. Okay, so from now on I'm going to base discussion that we have some iron 3 in the solution, and then we're going to address the whole problem. All right. So first of all, let's discuss how we get hydroxide in the deposit. All right. So this is our electrode. And here at the interface, our iron 3 plus times OH minus at the interface power 3 is bigger than Kp, bigger than product of solubility. So what really happens is that I'm going, if those are grain boundaries, etc., grains, and I'm growing deposits from nucleating here and here and here, and these nuclei grow. Here the grain boundaries, because it's also a convenient place for heterogeneous nucleation, are also going to have nucleation of the oxide phase. Small oxide phase will nucleate here. Now, this oxide phase will eventually start to grow too and get bigger a little bit and bigger, but because it covers the surface, the electron transfer through this oxide will be much more difficult because iron hydroxide is kind of not really conductive. And so what's going to happen is that surrounding nuclei of metallic phase will outgrow this and eventually trap it in the deposit. And so likely is that what you're going to have is the film where you're going to have some grain boundaries, and along these grain boundaries there will be a lot of oxide, or actually hydroxide phase, which is trapped during the growth. There will be oxide phase in the grains too. But this is reality, this is what you're going to get. All right. Now, when we talked about nucleation, we didn't talk about nucleation only because of electrodeposition. Generally, nucleation phenomenon occurs whenever you grow a new phase. But what we really discussed is that nucleation rate in terms of the thermodynamics, J, is some constant times E to the minus. And then we have some numbers, I'm going to say constant, but then it will be gamma power 3. Then there will be molar volume power 2. There will be KT, and there will be delta mu square, if we remember. Now, this delta mu square is the saturation that we discussed, if you remember. And the saturation means, what's the free energy change between the one phase to another phase. Obviously this term comes from the creation of new surface. We talked about it. I don't want to repeat myself. Now, we said that delta mu is minus NF eta, which is for electrodeposition. But when we do have crystallization or precipitation type of the new phase growth, this delta mu is defined in terms of the KT ln S. Now this S term also is called supersaturation, etc. Let me explain you what this S term is. In terms of our discussion, I'm going to simplify it a little bit, but the S term here is actually the ratio, and I'm going to focus only on iron concentration for the moment, although you could be more elaborate, between the iron 3 plus concentration at the interface and iron 3 plus concentration equilibrium, which is the one that you can calculate for the known concentration of OH from the product of solubility, right? So this equilibrium concentration, iron 3 plus in equilibrium, which means the threshold. Below that, no precipitation. Above that, precipitation, is basically Kp divided by OH minus power 3 equilibrium, right? Now, having said this, I'm going to reverse the story and say the nucleation rate of my hydroxide phase, meaning I can ignore everything here. Well, actually, if I put this Kt ln S, instead of this, it's going to be Kt power 3, and then it's just going to be ln S. So we can say that nucleation of our hydroxide is proportional to some constant times e to the minus, and it will be a constant that is multiplying, and then I'm going to say 1 over ln S power 2, right? What I'm really doing is just replacing this term with this term, and I'm ignoring all these things that really don't matter, and I'm just writing this, okay? That's the nucleation rate. Now, nucleation rate is, as I discussed with you guys, it's 1 over centimeter square second, right? So number of nuclei per second per area. Now, if we assume that every of these nuclei formed will grow to some size which is proportional to some number of moles before it gets buried, because I nucleate here, but you know, they eventually, due to the dynamics of the growth of the surface, will grow to certain average size, which is number of, you know, size in terms of number of moles of that. Then I can say that incorporation rate, and I'm going to call incorporation rate R, hydroxide, right, is proportional to the average size of the incorporated nuclei times the nucleation rate, which is basically m times A, which is the nucleation rate constant, e to the minus some constant here, 1 over ln S power 2, right? That will be the rate, and the rate, obviously, if this is moles and the whole unit of this is 1 over centimeter, so it basically has a unit of flux, which is mole per centimeter square second. So we are doing a little bit of the trick, assuming that every nuclei that is in form grows to a certain size and incorporates. And so basically, for that reason, incorporation rate is proportional to nucleation rate and times this average size of the hydroxide. That's the whole story. Now, once we have this, let's go back and look our interface. Now, actually, I'm going to do it here. Or actually here. So this is our interface, electrode, solution, and H plus at the interface is equal to H plus bulk minus 1 minus gamma I delta over F times dH plus, right? Okay. The OH at the interface, OH minus at the interface, is equal to what? Kw divided by all this thing, which is H plus bulk minus 1 minus gamma I delta F dH plus, right? Okay? Because we use the ionic product of water, and we just divide that with the concentration of hydrogen at the interface, which is this term here, and we get the OH minus at the interface, right? Okay, so now I know what this OH minus at the interface is. For a process that has this gamma, that has this current density, this diffusion layer thickness, etc., right? So next step, it's very simple. Let's figure it out. What is the maximum amount of iron 3 plus that I can have at the interface just prior to precipitation? Meaning, you know, what's the iron 3 plus equilibrium at interface? Well, it's basically Kp of iron 3 plus divided by this thing here, which is Kw, and this whole thing comes up, which is the basically H plus bulk minus 1 minus gamma I delta F d H plus. But because this have to be power 3, this will be power 3, and this will be power 3, okay? So that term here, when you look at the definition of this S, which I wrote somewhere, but I told you S is this, which is the concentration at the interface, and this is this equilibrium, which is the maximum allowed one before I see any precipitation. Okay? So now I know this is equal to this for our process, for delta, current density, and gamma. We know what it is, okay? But the question is, what is this iron 3 concentration at the interface? All right, that's a very simple thing. What could happen with iron 3 in a solution? Let's discuss that. I'm going to go back to this equation, but I just want to explain it. Well, I can have an electrode, right? And solution, our interface. So I have iron 3 plus here. Comes nearby the electrode surface. It's negative potential cathodic reaction. What could happen? It can be converted to iron 2 plus electron, right? So some part of iron 3 plus could be actually, if this is the bulk solution and this is Fe3 plus in the bulk, the interfacial iron 3 plus should be to some extent smaller, because you know it's reasonable to expect that there will be some reduction of iron 3 plus to iron 2 plus. It's a negative potential. The reverse, the equilibrium potential of iron 2, iron 3 is way more positive. So if you're on negative side, you should expect this happen. Okay? Everybody understand this? So part of iron 3 is converted to iron 2 during electrodeposition. Part of iron 3 is trapped in FeOH3 precipitate, right? So definitely iron 3 concentration at the interface should be smaller than iron 3 plus concentration in the bulk. Am I right? Should be. We should expect some depletion because we are precipitating iron 3 hydroxide, plus there will be some conversion into iron 2 at the negative potential, so the cathodic process that we do electrodeposition, right? How are we going to model this in a way mathematically to take this into account is very simple. You see this, so I define S as the ratio between iron 3 plus at an interface divided by iron 3 plus equilibrium at an interface, right? I don't know what it is, but what I'm going to say is that this is equal to some P iron 3 plus in the bulk divided by iron 3 plus equilibrium at the interface. What is this? P is some number smaller than 1 and bigger than 0. Because I expect to be smaller than the bulk, right? So now, going back to this expression, which I said that incorporation rate of my hydroxide is equal to this average size of my nuclei times nucleation rate constant times e to the minus, and there will be some constants here, which we are not really interested in writing, 1 over, and there will be ln, and then instead of iron 3 at an interface, I will write P times iron 3 plus in the bulk. And here, instead of iron 3 equilibrium, I will write this, Kp over Kw power 3 times this on power 3, okay? So it's going to be a little bit Kp over Kw power 3 times and ln S has to be also power 2, and here will be H plus bulk minus 1 minus gamma. It's going to be a big minus gamma times I times delta over F times dH plus. This is power 3, but then the whole, this thing here has to be on power 2, okay? So now I have an expression for hydroxide rate incorporation in moles per centimeter square in second, and this is basically some constant, we don't know what it is, and then it will be a function of the process parameter current density, diffusion layer thickness, concentration H plus in the bulk, which you can write as a 10 to the minus pH. So, you know, H plus in the bulk is equal to 10 to the minus pH of the bulk. You know that pH is the negative logarithm and so on. And so on. So you have expression that tells you at what rate hydroxide actually incorporates into your deposit for a given process parameter such as current density, diffusion layer thickness, and gamma, which is the efficiency, current efficiency. So that's what it is. All right. What do we do with that? Obviously, I don't know this. I don't know this. These constants that enter this exponential term, which is Vm, surface energy, you can have a good, reasonable estimates in the literature, etc. So you can basically get that. So the main thing is, you know, I don't know this P and yeah. So basically, you can think. I don't know even this, you know. So this is all one constant. Basically, I don't know it. Okay. So you have basically two unknown constants in our model, right? Okay. Let's discuss what we can do with magnetic element. We can measure magnetic moment. Magnetic moment is tricky measurement. It requires, because when you measure magnetic moment, for example, using VSM, what you really do, you measure magnetization, and then you have to divide this magnetization with volume of the film, and then you get B sub S, which is saturation magnetic moment of the film, right? So you need to know accurate dimensions, meaning thickness and width, you know, volume of your film. That's number one. Number two is that if you would have a perfect material, for example, and I'm going to use here, I think I sent you material where you have ternary diagram, but you know, there's a phase here, which is about cobalt iron 50-50. and it has a 2.4 Tesla magnetic moment. So if, let's say, I tune my process, let's say with my concentration of iron and cobalt in the bath at the current density, that should give me a roughly 50-50. You know, plus minus 2% don't matter here, moment should be 2.4 Tesla. Then if I have no oxide phase, for reasonably accurate measurement of the volume, you know, dimensions of the film and magnetization from the looper measurements, etc., I should get probably B sub S, if it's a pure film, 2.4 plus minus 0.5 Teslas. Yeah, this is an error type bar that I'm making, you know, because estimate of the volume is not always spectacular and so on, right? But this is what you get if I measure the saturation magnetic moment of these alloys with no oxide phase. However, if this exists, meaning if this thing here, P times this is divided by this is bigger than 1, because ln of 1 is 0, but ln of less than 1, it doesn't have any physical meaning because you don't have precipitation. But if it's a bigger than 1, that means this concentration P times this is bigger than this, that means I'm precipitating. So if this happens while I'm doing deposition, what's going to happen, I'm going to get iron hydroxide phase, which is paramagnetic at room temperature. Magnetization is close to 0. Which means that the magnetic moment of my film, which I think is cobalt iron plus some oxide phase, will be basically 2.4 Tesla times 1 minus alpha iron 3 hydroxide. And iron 3 hydroxide is the volume fraction of this oxide phase. Now I have a rate, which is mole centimeter squared per second, but I need volume fraction. How I'm going to get the volume fraction? All right, so bear with me, I'll explain just in a moment. So, considering that we're growing a film, and there's a little incorporation of oxide phase, the volume fraction, roughly, alpha, iron 3 hydroxide. I mean, I can give you a clear formula, which is longer, but I'm going to just say, is approximately the rate of incorporation of the hydroxide phase, then the rate of deposition of cobalt iron phase, times, because this is the rate, and I want to get the volume, you know, this has to be multiplied by the molar volume, and you get basically the ratio in terms of the dimensionless number, such as fractional volume, okay? All right, so what do I do? Well, I can actually measure this, and I can create the model that will take care into account this, which I can calculate from this formula. Rate of cobalt iron is a constant, molar volumes of each phase we know. So basically, just the model will be here instead of, you know, this, right? So let me show you how this really looked like. I need to get rid of this writing, so you guys probably caught up, right? So it's really interesting. So what we do experiment is kind of cool thing, because you will see that suddenly the model and theory, everything looks pretty cool and pretty good. And Peter, thank you for taking care of the board, by the way. I see it's been cleaned up and nothing sticks, so it's pretty good, thank you. So what do? We measure B sub S of our samples, and here each sample is produced with different iron 3+ concentration in the bulk. So we controllably add iron 3 in the bulk, right?
So what happens? This is 2.4 Tesla, and so for very small concentrations, really nothing happens.
It's 2.4 Tesla every sample we measure.
At one point, when we exceed this certain concentration, I'm going to put star in the bulk, and this star in the bulk is equal to, if you really want to know, is basically it's Fe 3 plus concentration at the interface divided by this P
parameter, because P times this is equal to that. If you remember the discussion I said.
You're going to start to see suddenly, really large decrease, and then kind of levels out, and this is 1.3 Tesla.
So you get about decrease over close to 50% after this, I'm going to call this star, concentration is exceeded, which is super small, by the way. It's a function of pH of the solution, etc., etc., etc. But this is what you get. Now, this model,
B sub S is equal to 2.4 Tesla 1 minus, and this alpha is basically R hydroxide times Vm of hydroxide divided by R cobalt iron, Vm cobalt iron. And this thing we have equation for. This is constant, we know for the process, etc., etc. And so when we fit this model here and here and here, we get something like that.
The only fitting parameters in this model, whether you appreciate or not,
P becomes 0.95,
very close to 1, which means really small depletion of iron 3 at the interface.
and this nucleation rate constant, which is Nm times A, this constant gets some number,
By the way, it has a physical meaning, and it tells you, gives you an idea how big average nuclei could be, etc. But I'm not going to go into this because they're very small, etc. But the bottom line is that P is very close to 1. So you almost would not make a big mistake assuming that P is equal to 1. Almost no depletion of iron 3 at the interface. But let's keep it, what it is, okay, so you understand. That's very important. So now you have your process for the current density, solution design, pH, whatever, we discussed. You have your data where you controllably entered in the solution iron 3. You fit your model to the data, and now you have your P. Guess what you can do now? Now you can simulate your problems. For example, if you look this equation, I just want to show you. You can see that in the model, pH of the bulk, concentration of iron, concentration of hydrogen in the bulk, which is your pH measurement, is something that is part of the whole equation. You can now say, what if my pH probe is not reading correctly? What it really means is this. I can have a look how this looks like. If this is, for example, for pH equal 2, how this is going to look like for pH equal 2.1. And I can calculate using this same thing. And for pH 2.1, it's going to look like this. For pH 1.9, it's going to look like this. So now I can see if I'm reading, if my pH reading is 2, but it's actually 1.9, actually I'm in a safe place, because if I think my iron 3 concentration is here, actually my region of stability is extended, because the lower pH gives me an extra ability to run the process, because the depletion of hydrogen plus ions at the interface is not so severe, so OH minus is not so high, right? But if my pH probe gives me wrong reading, and instead of 2, I'm reading it's 2.1, and I think I'm here, and I think I'm doing okay because I should be getting 2.4, guess what happens? I'm here. None of the devices is good. Okay? We can reverse the story, because here in this equation, or actually if you can see, there's a current density. And I told you when you try to plate in the recess like this, because of the field concentration, the current density in this recess is not the same as current density in open space. Here it's I that we think we have. Here is some I prime which is bigger than I. It's called current crowding effect. Well, same thing. I can now have my model everything the same, but I can simulate the curve with a little bit higher current, 10% increase, and a little bit lower current. A little bit higher current, if this is your process, I naught, your higher current, which is 1.1 I naught, will be here, and this will be 0.9 I naught. You can see lower current density will push you further, which means you're going to have way much more tolerance for Rn3 plus in the solution, while if you have a current crowding problem, you will have way less tolerance for Rn3 plus in solution. You can also simulate the effect of mixing. Let's say this is stagnant electrolyte, delta diffusion layer is about 0.05 centimeters, but if you do mixing, it could be less, and you can simulate curve, and you're going to get about the same but opposite effect than the current density increase, because this increase will basically similarly show up here, right? So this is what is important. So when you do electrodeposition of magnetic alloys, this process is with you, and you have to be aware how you design your process in terms of having iron 3 plus in the solution under control. Because if you're above, your magnetic moment will be less. Now, for the same reason, instead of measuring the volume fraction, we can measure the oxygen fraction, or just a fraction of the magnetic alloy. And so that really means if I say oxygen fraction, it will be some constant times the ratio between incorporation rate of the hydroxide versus the incorporation of the cobalt iron, for example, right? And I can generate another measurement. Instead of measuring the magnetic moment, I can measure percentage of oxygen as a function of iron 3 in my solution. And obviously, there will be some residual content of oxygen which is unrelated to iron 3 hydroxide precipitation, which could be trapment of the ions, sulfates, whatever. And then suddenly, as soon as you exceed this iron 3 plus concentration star, what's going to happen? You're going to have something like this. And again, you can devise your model from the rate of incorporation and fit to this, and you will get pretty much the same numbers and so on, right? Then, which is really cool, is that you can plot coercivity as a function of iron 3 content, and coercivity will be actually showing you this kind of a behavior. Okay, this is coercivity and this is iron 3. And if you plot coercivity versus oxygen content, for example, it will show you some other thing. But what you're really doing this way is having a quality control over your deposit in terms of the magnetic moment and coercivity, which are two most important parameters when it comes to soft magnetic alloys, assuming that your composition and everything else is taken care of according to the process. And so with this, there is another thing that I want to tell you is that sometimes when we run this is DC deposition process, and we expect to run the process where H plus at the interface never goes down to zero, right? Because if it goes down to zero, you're in trouble, you're going to precipitate any hydroxide, right? So in this particular case, the balance is such when we do electrodeposition that, you know, H plus at the interface will be bigger than zero or will be much bigger than zero because otherwise there's no point discussing, right? However, when we do pulse deposition, there's an unsteady state, which means before we turn on the potential, it's H plus in the bulk. And then for the given current, as we are waiting, the concentration drops down and becomes some H interfacial, which is lower, right? And we have these equations for the unsteady state and so on. So the thing is also that you can do is calculate how long you can pulse, or I mean how long your pulse current should last before you encounter a situation where interfacial concentration of hydrogen plus is lower than allowed for precipitation of nitric hydroxide. And that can serve as a parameter for your pulse deposition cycle calculation, basically. And so, and you can do a lot of other things. But overall, with this, we're going to conclude oxide stuff. And I'm going to give you a project. And next time I'll show you some interesting work, which is going to be just intro before we go and talk about some other things. Do you guys have any questions?
How do you get the E value? Since we have two unknowns, so how do you get the model? Because we get the rating operation, but it has two unknowns, right? So
Fit.
the E value.
Yeah. But so you have a bunch of the experimental data, right? And you fit your model to experimental data, and you extract these two fitting parameters, P and this and A, okay? That's why, you know, this is how you learn your process, right? And P is close to 1, almost. You can almost say it's 1. It's not going to affect you much in terms of understanding. And the only thing that you come out is this constant, right? Everything else, more or less, it's fine in literature. And material I sent you basically gives you even more elaborate and deep discussion in terms of the shape factor and stuff, which I avoid because we assume it's a hemispherical nuclei, 45 degrees wetting angle. This stuff that I have in papers is a little bit more elaborate in that sense that it could be any shape and whatever, but you will understand what I'm talking about. But, you know, this topic, nobody will tell you. And what you learn from these last two classes is actually very important if you're ever going to go into magnetic alloy electrodeposition, because more or less everything else that you can hear is the knowledge. It's a knowledge which, you know, you don't have to be really trained or something, you figure it out. But these kind of tricks and this kind of details you can only get in a graduate class. So, and again, depends what kind of alloy you want. Sometimes if you want them to be resistive, but the moment is not the most important thing. Well, you can probably live with this type of the moment, but they will be super resistive because they're going to have a lot of oxide incorporated, which is electron scattering phase for the current flow. Any questions?
How hard is it to get oxides instead of hydroxides in electrochemistry?
Come again?
How hard is it to get oxides and Fe2O3 and FeO instead of hydroxides when you're doing, like, usually you never get like Fe2O3, all those things.
So FeOH3
or iron 3 hydroxide is basically Fe 2O3 times H2O, because if I put here, then so 3 H2O, so it's the same thing. It's a hydrated Fe2O3. So if you have a hydroxide and you just heat it up, you end up with Fe2O3 where the water is liberated. If you let it cool and the moisture in the air is significant, it will rehydrate again. It just basically there's an equilibrium between hydrated, so that's what it is. And FeOH2 is basically FeO plus H2O, so basically, yeah, so if you heat it up, this hydroxide, you're going to get FeO. Right. So no problem. But this kind of stuff is, I mean, chemists, organic chemists know for this kind of stuff. If they produce the iron oxide for whatever reason they do, but they use iron oxide for a lot of interesting stuff. Am I right? It's a semiconductor. It could be used for harvesting light, right? All sorts of stuff. I don't know. Randy is making iron oxide particles.
Yeah.
They use them also for biochemist as a carriers for drugs and stuff. I mean, what I'm trying to say, you know, there's a whole field about that, which is not the subject of the course, right? Okay, so then I'll see you guys next week. In the meantime, expect my email with the project.